Finally, we want to go from 6 to 10 seconds. And it looks like that at 10 seconds, I have my object at a position of 9.5 meters. So let's figure out now what the average velocity is during that time interval. So we're looking for the slope of the line that connects those 2 points. Again, we're going to say x final is 9.5 meters. X initial was 2.5 meters. That's where I began moving at the start of this time interval. We ended at 10 seconds and we began looking at 6 seconds. So now we'll put those numbers into the calculator. During this time interval, the object moved with an average speed of plus 1.75 meters per second. Next example. This graph gives a plot of velocity versus time for an object moving along a straight line. A, what was the average acceleration between t equals 20 seconds and t equals 60 seconds? And B, what was the average acceleration over the entire 115-second time interval? All right, in part A, we want to start at t equals 20 seconds, and we want to go to t equals 60 seconds. Now notice, we have a velocity versus time graph. So what this graph represents is not where the object is, but how fast and which way the object is moving. So what this says is that my object started at 20 seconds, moving at a speed, it looks to me like, about 25 meters per second. And ended up at 60 seconds moving with a speed of about, let's say, 31 meters per second. We're trying to figure out what is the average acceleration. So we're trying to find the slope of this line that connects those 2 points. We'll use our average acceleration formula. The average acceleration is equal to the change in the velocity divided by the time interval. The final velocity was 31 meters per second. The initial velocity was 25 meters per second. The final time was 60 seconds. The initial time was 20 seconds. So my time interval is given by that difference that's in the denominator. Now let's go to our calculator. And what I find is that my average acceleration is plus 0.15 meters per second per second. In other words, in every second, on average, I gained speed of 0.15 meters per second. We'll come to call that meters per second squared in future lessons. Now we want to figure out the second part. What was the average acceleration over the entire 115-second time interval? Well, let's start at t is equal to 0, and let's end at t equals to 115 seconds. And now what we're trying to find is the slope of that line that connects those 2 points. I can see that this is going to have a negative slope because I end up with a slower speed than I started out, a less positive velocity, if you want to think of it that way. It looks to me like that we start out with an initial velocity of, let's call that 14 meters per second at time 0, and here I have a speed, it looks to me, let's call that about 7 meters per second at time 115 seconds. So we want to find what's the average acceleration during that time interval. What's the slope of that line? So now put in the numbers. I ended up at 7 meters per second. I started out at 14 meters per second. The time interval is 115 seconds minus 0 seconds. And now we substitute the numbers. I get negative 0.61 meters per second squared. Now, certainly this slope doesn't represent the entire graph. What it does tell me, though, is that on average, if I look at the entire motion of the system, on average, if I see where I ended up, I see how fast I started moving and what the time interval was, then I can figure out what the average acceleration is. One more example. The velocity versus time graph of an object moving in a line is given below. A, find the object's displacement during the first 10 seconds. B, find the object's total displacement during the 20-second time interval. All right, now instead of working with slopes, we're having to work with areas, because we know that the displacement is the area between the graph and the time axis. So essentially what I need to do is I need to figure out what is the area between the graph in this section right there. That seems like a daunting process, except I see that I could probably break my graph into two parts. If I go to right here and approximate this first section right there as a rectangle that's got that area, and then approximate the next section right here as a triangle, I could find the area of those two objects. The area of a rectangle is equal to the base times the height, and the area of the triangle is going to be equal to 1/2 of the base times the height. The base in this case is how much time are we talking about. So in this first section right here, the base is 5 seconds long. And in the second section, the base is also 5 seconds. Now I've got to figure out what the height is. In the first case, the height is going to be, well, it's actually going to be a depth if you want to think of it. The height is going to be -8 meters per second. And likewise, the height in the second section is also going to be -8 meters per second. So I need to put those two things together. So what I want to say is that this area is going to be, the total area is going to be the area of the first part plus the area of the second part. The base times the height of that rectangle plus 1/2 of the base times the height of the triangle. The base in this case is 5 seconds. The height is -8 meters per second. So there's the area of the rectangle. The area of the triangle is 1/2 of the base times the height. And now I'll put those things together. I have -40 meters. You see that this seconds cancels that seconds, and I end up with meters, plus -20 meters, so that the total displacement in part A is -60 meters. Now, I don't know where the object started. This graph doesn't tell me that, and there's nothing stated in the problem statement that tells me where the object began. But wherever it started, it ended up 60 meters farther away from the origin on the negative side than where it started. If I've started on the positive side of the origin, then that means I'm 60 meters closer to 0. If I started on the negative side of the origin, that means I'm 60 meters farther away from 0. But whatever case, I went in the negative direction from where I started. Now, part B says find the object's total displacement during the 20-second time interval. We found how far the object went in part A. Let's figure out the object's displacement in part B. And in order to do that, I've got to figure out what is the area that's underneath this part of the graph. Now some of you can spot and say, oh, this is a symmetric system. And since I have just as much area on the positive side in the second part of the graph as I do on the negative side of the first part of the graph, then I'm going to end up at my starting point. And you would be absolutely right. But let's do this in the same way, a similar way as what we did in the first part. So let's break this into segments. I have a segment that's right here that looks like it's a triangle. Let's find the area of that triangle that has a base of 5 seconds and a height of +8 meters per second. And then let's go to the second part and let's find the area of this rectangle, where the area is going to be the base times the height. Again, a base of 5 seconds and a height of +8 meters per second. All right, so we're interested in starting at t equals 10 seconds and find the area of from 10 to 20 seconds. The displacement is going to be 1/2 of the base times the height. That's the area of the triangle. And then the area of the rectangle is going to be the base times the height. So this is going to be 1/2 of 5 seconds times +8 meters per second, because the height of this triangle here is 8 meters per second if you look over on this velocity axis. And now I need to add the base, 5 seconds, times the height, 8 meters per second, of the second part of this rectangle that's over here. And now when I do that, I end up with +20 meters. plus 40 meters. So I end up with plus 60 meters as the displacement for between 10 seconds and 20 seconds. Now the total displacement is going to be the sum of those two displacements. So it's going to be A from 0 to 10 seconds plus A from 10 to 20 seconds. So the displacement is that area, negative 60 meters plus a positive 60 meters, which is equal to 0 meters. In other words, when I stop my stopwatch at t equals 20 seconds, I find that I have gotten back to my starting position. So, recapping, in this lesson what we've done is we've looked at characteristics of motion graphs. We've seen that we're looking at position versus time, velocity versus time, and later on we'll come to acceleration versus time. We have computed from one thing, looking at lines and areas, other things from the graph. We've computed the average velocity from a position versus time graph. We have computed average acceleration from a velocity versus time graph, and we have computed displacement from a velocity versus time graph. For now, that's it.